So we left off talking about a few ways that we can think of segments inside of triangles, and we're adding some in 5.4, and we're talking about medians and altitudes. Let's skip down to the definition of what we mean by a median. So a median of a triangle is a segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side. So triangles' three medians should always be concurrent. So we've seen a couple concurrencies already. Medians will be another. So the way I'm going to use concurrencies with a median, and again, if I tell that these are medians, for example, if I have D to J there, so segment DJ, that'd be a median because I'm going from a vertex of the triangle D to the midpoint of the opposite side at J. So I have another one from E to G, I have vertex to midpoint, and also from F to H, that's vertex to midpoint. So the way I'm going to use those medians is that when they are concurrent, I know that the distance from the vertex to the point of concurrency is 2/3 of the length of the entire median. So for example, the length from D to C, that's from the vertex to the concurrency. That's 2/3 of the distance from D to J. Same thing if I do from E to C, that's 2/3 of the way from E all the way to G. And last one is that from F to C, that's 2/3 of the median from F to H. So 2/3 is the part from your point, so your vertex to your point of concurrency. The point of concurrency of the medians that we just used there, so that point C, we call that a centroid. That's going to be the centroid of the triangle, or also we could call that the center of gravity. Call it center of gravity because if I put that into a real life triangle, that's where that triangle would kind of rotate and balance around that point C. For any triangle, the centroid's always got to be inside the triangle, so we've seen some examples of other points of concurrency where they don't have to be. But yes, the centroid should always be inside your figure. And also, if I try that with a few practice questions, for example, if I'm given the length of XA, so XA is from the vertex to your centroid, I also want to use that to find the length of the segment from X to B. So we are given part of it, we want to find the whole length. So I can just remember that if I'm going from the vertex to your centroid, so from X to A where the points meet, that's going to be 2/3 of the distance from X all the way to B. So again, from your vertex to the centroid is 2/3 of the entire median. So if I just plug in XA, that length is 8. So if 8 is 2/3 of XB, all I got to do there is multiply by the reciprocal, and we get that the length XB should be 12. If it makes it easier for you to not use XB and just use maybe like X or Y as a variable, you just won't want to think of these as being two separate variables. XB is just the length of that median. A similar question for part B. So if ZA is 9, that's from the vertex of the median. That should be 2/3 of the length from Z to C. So if I want to find the length of ZC, I set up a similar equation. 9 is 2/3 of that length from the median. So if I multiply by 3/2 again, I get that should be 13.5 or 27/2. Last question, what's the ratio of ZA to AC? So ZA is that same distance from your vertex to the centroid. And then AC is the distance that should be shorter from the centroid to the midpoint of the opposite side. And that ratio should be 2:1. And that's, I think, a lot of times the easier way to think of this in terms of your ratios. Whatever length I have from the vertex to the centroid, it's always going to be twice the length of the other part of that median. So if I have that ZA is 2/3 of that distance, that only leaves AC as being that last 1/3. So that ratio is 2:1. We talked about medians, so now if we're talking about altitudes, that's the perpendicular segment from a vertex of the triangle to the line containing the opposite side. So let's first of all see what that looks like in our figures. Or I guess we'll add that into an altitude of a triangle can be inside, outside, or on a side of the triangle. We saw that with, I believe, circumcenter. Could be outside, inside, or on the side. So the lines that contain an altitudes are also concurrent. So another point of concurrency that we can use here. So we see our different examples. If I try and find altitudes in an acute triangle, notice I start from a vertex and I go perpendicular to the opposite side. Doesn't have to go through the middle of that. I don't have to go and bisect that segment. I'm not looking to make a perpendicular bisector, just to go from a vertex and make it perpendicular to that opposite side. Same thing if I'm going from this vertex, perpendicular to this side, and from that last vertex perpendicular, I see that that point of concurrency is inside the triangle. So if a point of concurrency can be inside a triangle for an acute triangle, we see that when I try to make a right triangle, going from this vertex to this opposite side, that's perpendicular. This vertex to this opposite side, that's another perpendicular. I actually have two altitudes that just form the sides of that right triangle, and your third altitude goes from this vertex perpendicular to the hypotenuse. So in this case, if I have all those points of concurrency meeting right here, that point would be on your right triangle at that bottom right angle corner. So same thing, if I try that again with an obtuse triangle, I see that my point of concurrency can actually lie outside that triangle. So if I have acute, right, or obtuse, I can be inside on the triangle or outside with that, the point of concurrency. So if I want to identify which is which, choosing between a median and an altitude, in this example we're asked if PR is a median and altitude or neither. And if I look at segment PR here, P goes from a vertex and it goes perpendicular to the side which contains, looks like I cut that off there, but that should be side PS. So that should be an altitude. Again, altitude doesn't have to be within your triangle. I can just draw it straight down, extend this side so that it makes a perpendicular. That would be your altitude. So again, from a vertex, perpendicular to the line containing the opposite side right here. If I look at QT though, so Q is this point in the corners from Q to T, that should be a median because I'm going from the vertex at Q and going to the middle of the opposite side. So from vertex to midpoint, that should be a median. And there's also one page as practice. I think I'll actually skip through that page. So you do want to try that last page of 5.4. Try that on your own, see if you can get those, and if not, you can ask about those in class, but do try to have those practice problems done. 5.6 is adding in, finally we aren't dealing with things that are equal in our triangles. Now we're looking at inequalities. And first inequality that I see here is that if two sides of a triangle are not congruent, so again, if one's bigger than the other, then the larger angle should lie opposite the longer side. So you think bigger angles should go with bigger sides. In that example, if I say that xz is bigger than xy, so let's say xz is a distance of 3, and let's say xy is 1, for example, that means if this is the longer side, xz is bigger than xy, that means the angle across from your longer side, that's angle y, should be bigger than angle z. It doesn't tell us what those angles are, it just tells us that angle y is bigger than angle z because it's opposite the longer side. So that's our rule. Larger angle should always be opposite the longer side, which means you can just flip that around as well. I can take a converse and say that if two angles of a triangle are not congruent, so this time not the sides, but let's say if angle A is bigger than angle B, so let's say angle A is 100 degrees, and let's say angle B is just 20, for example. If I have angle A, which is 100 degrees, that means the side opposite angle A, so side BC here, so yeah, side BC should be your longer side compared to the side opposite angle B, which is AC. So if it's a side opposite a bigger angle, should be a bigger side opposite that. So BC is bigger than AC. So similar sort of rule, the longer side is always across from your larger angle. And if I try that, I think we have some practice, if I can get to that. Yep. So our first problem is where I have a park and I'm trying to pick in this first example, for part A, which two streets will form a corner with the largest angle? Again, as soon as you see largest angle, we don't really have a lot to go on other than the side lengths. I want to find the largest angle by looking at where your longest side is and going opposite that. So my longest side looks like Hollingsworth Boulevard. That has a bigger distance than the other two. So if I want to make my largest angle, I should go opposite that side, and that would be where MLK meets Valley. So MLK and Valley would be that right corner. Because that's opposite my longest side, that should be my largest angle. If I then look for the second largest angle in part B, similar sort of steps, now I just can't choose this angle that I chose first. If I'm choosing between the last two, I want to choose this angle over here where Hollingsworth and MLK meet because that should be opposite your second longest side, which is Valley. So that leaves our shortest angle would be opposite our shortest side. If I try that again, this time we have some missing information in problem 2. First thing you want to do, anytime you have two angles in a triangle, you can always get more information by taking 180, subtracting the two that you know. You should always be able to figure out that third angle. So that's going to be coming in handy a lot on these questions. And the first thing you want to do is find that missing angle. So if I take 180, subtract 62 and 58, that means the angle that wasn't listed at the start should be 60. So now if I'm looking at these sides in order from shortest to longest, my shortest side should be across from my smallest angle. So from this angle 58, opposite that should be side TV. That's my shortest side. Next smallest angle is 60, so opposite that is my next shortest side, UV. Biggest angle is 62, so longest side should be UT or TU. If I try that again, same idea. If I'm given 2 to start with, 24 and 130, I do want to find angle x just to be sure. I want to subtract 180 minus 130 and also minus 24. That leaves us that x should be 26 degrees to finish that triangle. And now if I'm looking for my shortest side, that was important because since the 26 is bigger than 24, for my shortest side, I want to look opposite the 24, and that should be side OX. So OX is the shortest side. It's opposite your smallest angle, now that we figured out all 3 of those angles. So looking to our last page here, for 3 segments to form a triangle, I need to relate them in a certain way. And if I see that example here, so we see an example where I do not have a triangle form. So I have one example where, yes, this is a triangle that's formed, and one where I still use 3 lengths, but that doesn't form a triangle. And the rule behind that is the sum of the 2 smallest lengths have to be greater than your greatest length. So if I add 3 and 3, that's bigger than 5, so that works for that first triangle. But if I add 2 and 2, those are my 2 smallest lengths, that's not bigger than 6, so I can't form a triangle with those. So that leads us to our triangle inequality theorem, which kind of generalizes that. It just says the sum of any 2 lengths of 2 sides of your triangle should always be greater than the length of your longest side, or third side, but really you do want to compare it to the longest side. So that works for any combination. X, Y, and YZ should be bigger than XZ. Also, if I take YZ plus XZ, should be bigger than XY. And also XZ plus XY should be bigger than YZ. So it should work for any sides. But really what you got to do first is always look at the 2 smallest, add those, and see if they're bigger than your third side. So if I want to see if these triangles will work with the given lengths, I know that the first situation will work because my 2 shorter sides are 3 and 7. Add those up, that's bigger than 8. Don't really even have to test the other 2, but it's always good to include that. 7 and 8 is bigger than 3, and 8 and 3 are bigger than 7. So since all 3 follow the triangle inequality, that would be a triangle that's possible with those lengths. Next situation, if I add my 2 smallest lengths, 5 and 10, that's equal to 15, but I want it to be greater than 15. So that would not form a triangle because those are not greater than 15. Doesn't matter if they're equal. Last 2, if I add the 2 smallest, 2 and 6, that's not bigger than 9, so right away I can tell that that's not going to form a triangle. When I do know the lengths of 2 sides of a triangle, I can determine the range of possible lengths for that third side. So to find the smallest lengths, what we're going to do is we're going to subtract the 2 and take the absolute value. It's basically finding the difference between those 2 lengths. To find the largest possible length, we're going to add those 2 given lengths together. So if I want to put that into a single expression, if I'm given sides A and B, to find that third side length C, again, the smallest value is going to be the absolute value of the difference between the 2 that you're given. The largest value would be the sum of the 2 sides that you are given. So let's try that with some examples. If we're given lengths of 5 and 8 feet, again, we want to find a possible range that would work. So we don't really have to call it C, I just called it X in that example, but the smallest length is when I take the absolute value of the difference of those 2. So 5 minus 8 is negative 3. Absolute value is 3. That's the shortest boundary on my sides. And also if I add the 2, 5 plus 8 is 13. So I know that if I'm trying to form my triangle and have it satisfy the triangle inequality theorem, that third side has to be between 3 and 13 feet. If it's smaller than 3, say like 2 plus 5, that's not going to be bigger than 8. If it's bigger than 13, so let's say 14, that means that 5 plus 8 is not going to be bigger than that third side either. So trying that one more time. If I change those given lengths to 4 and 7, it still works out the same way. The shortest possible sides, if I subtract those, find the absolute value, that's going to be 3. Add the 2 together, I get 11, so that means my third side's got to be between 3 and 11 feet. Anything else would not work. So make sure you have that last part done from that previous notes from 5.4. That practice should be filled in. But have these both ready to go with some questions when we come in next time.